Hello everyone, my name is Haoyu Cheng. Actually, I'm a new assistant professor at the Yale University in the Department of Biomedical Informatics and Data Science. So in today's talk, I will briefly introduce some of our recent work about how do we achieve the haplotype-resolved de novo genome assembly. So let's first have a look at what's the challenge for the de novo genome assembly here. So consider if we have the large genome, like the large human genome, including 2 haplotypes with 6 billion base pairs. So the current sequencing technologies can only produce millions to billions of the short fragments called reads instead of the full-length chromosome. So the key challenge here is how to reconstruct the genome from the large number of the fragmented reads. So if we consider this as a computer science problem, both the genome and the reads are equivalent to the string that only including AC and G, ACG and T, sorry. So it's actually a very fundamental problem in both the bioinformatics and the string algorithm. So in today's talk, I will briefly introduce some of the following topics. So first, I will talk about how do we achieve the haplotype-resolved genome assembly, which means the assembly algorithm could reconstruct both haplotypes instead of only one. And then I will talk about how do we achieve the single sample haplotype-resolved genome assembly. That actually, the single sample here is just means that we do not need the data from the other sample. We do not need the data from the father and mother. And then I will talk about how do we achieve the telomere-to-telomere hybrid genome assembly. The telomere-to-telomere actually is the ultimate goal for the de novo genome assembly, that we reconstruct the entire chromosome without any gaps. So let's first have a look how do we achieve the haplotype-resolved genome assembly with hifiasm. So we know that actually the human genomes are diploid. There are 2 haplotypes, that one from the mother called maternal haplotype, another from the father called paternal haplotype. They are highly similar to each other. In this example, the majority base pairs are exactly the same, so there is just one difference here that we call the heterologous allele. So the key challenge about the haplotype-resolved genome assembly is how to reconstruct both haplotypes that are highly similar to each other. So if we, for this example, if we have the 2 haplotypes, right? So there are many of the dots in red, they represent the paternal variants, haplotype-specific variants, and we also have a lot of the blue dots that represent the maternal variants. So most of the traditional genome assembly algorithms that just trying to output one collab assembly that is a mixture of the 2 haplotypes. It's not a real haplotype, and definitely losing at least half of the information for a diploid genome. And then, actually, several methods that are trying to reconstruct more information that they would like to output 2 assemblies. So one is a primary assembly, another is alternative assembly. But however, the primary assembly is still a collapsed assembly, and alternative assembly is highly fragmented, makes the downstream users and application hard to use it. So the ultimate goal for the de novo genome assembly algorithm is the haplotype-resolved genome assembly, or we call the phase assembly. So which means the assembly algorithm should output 2 assemblies, one for each haplotype. So this procedure is also called the haplotype phasing traditionally. So there are several methods that are trying to do that, but all of them cannot output the decent result for the high quality or large of the human genome. So before we figure out what's the limitation for this algorithm, actually, I will just trying to briefly introduce the typical genome assembly workflow. So basically, we have a lot of input reads here, and we have many of the sequence errors within these reads. So the first step about the de novo genome assembly is just trying to do the error correction to remove any of the sequence errors. So after that, we end up with many of the nearly error-free reads. So the modern genome assembly algorithm, we are trying to build an assembly graph. So in this example, I'm showing the string graph. So we could say that each of the nodes represents 1 read, and each of the edge represents the overlap between the 2 reads. So eventually, we got an assembly graph. So finally, the assembly algorithm, we are trying to clean the graph and get some linear result. So this linear result corresponding to the original genome. So we always call this linear result called context here. So we could say that it is very complex, including many of the computational technologies like the alignment, phasing, some index, or also it's very time consuming. We need to have some of the implementation technologies, techniques to actually reduce the running time. So although this workflow actually works well for most of traditional genome assembly algorithm, it has a limitation for the haplotype-resolved genome assembly. So the first limitation here is the overcorrection. So if we look at example on the left side, so we have the raw target reads in black, and it needs to be corrected. So ideally, the method should only use the reads that from the same haplotype to do the correction. But in practice, since the two haplotypes are highly similar to each other, actually their difference might be just 0.1%. So it is very likely that they mix the reads from both haplotypes to do the correction. So as a result, we end up with some of the overcorrected reads, so this is not the result what we would like to have. So another limitation actually mostly coming from the pre-binning strategy. So this strategy actually widely used for most of the current haplotype-resolved genome assembly algorithm. So I'm just still giving an example about this type of the strategy here. So if we have the reads here, then many of the reads in red come from the haplotype 1, and many of the reads in blue come from the haplotype 2. So the pre-binning strategy is trying to using some of the additional data. For this example, we use the parental data, like use some marker we call, in most cases, k-mers from father and mother's genome to separate all the reads into two sets, so one set for one haplotype, and then conduct the individual assembly. So in practice, actually, ideally, this method is quite straightforward. It should work well. But in practice, there are a lot of issues, especially for the mispartitioned reads, which means that one read from haplotype 2 actually is mispartitioned to the haplotype 1. So as a result, we end up with some very fragmented result. It is not the result what we would like to have. So to solve this issue, actually, we propose the hifiasm algorithm. The algorithm here, for the first step, is still the error correction, but we consider the haplotype information here. So it could help us to avoid overcorrection using the reads from the both haplotype. And then we conduct some regular genome assembly to build an assembly graph. So the final step is a graph tree binning. It's the main difference in comparison with other tools that we consider, additional consider graph topological information actually could help us to get some better result, while all other tools actually losing this information. So let's first have a look about how do we achieve the haplotype-aware error correction. So the key assumption for the correction here is that there should be fewer recurrent sequence errors. So for a target read here, that need to be corrected. So it's still like, for this example, that for the target read in black, that actually the hifiasm algorithm will try to identify all informative sites. So the informative sites here is just corresponding to some real variants or real heterozygous allele. So in this example, if we look at the target reads, so there are two dots, right? The dot in red at the left side actually is a real informative site. The reason is that there are multiple other reads supported. But for the purple dot on the right side, actually, it is very likely to be a sequence error since there is no other read supported. So after that, actually, the algorithm will try to collect all the reads that are identical at the informative sites. So this procedure is more like we do the haplotype phasing during the error correction and only use the reads from the same haplotype for the correction. So this definitely could help us to avoid the overcorrection problem. But in practice, it's introduced a lot of the additional computational costs. So in these cases, actually, we additionally using some of the SIMD-based bit vector algorithm to significantly reduce the running time. So after that, actually, since we have the nearly error-free reads and we keep all the phasing information within the reads, actually, the algorithm is trying to build an assembly graph. So we call this a phase assembly graph. It's just that we keep all the phase information. So if we look at the example on the right side, right? So we could find that each of the nodes is still the reads, and each of the edge is still the overlap between different reads. So eventually, we could say that all the reads in yellow and in blue, they are heterozygous reads. They could be separated into two haplotypes by the heterozygous allele. So, but for all the reads in green, actually they are homozygous reads. They collapse together since they are not long enough to cover any of the heterozygous allele. So eventually, we get some of this bubble structure, since actually in each side of the bubble, they are heterozygous, but on the two ends of the bubble, actually, they are homozygous. So for the large human genome, so ideally, we should have this type of the chain of bubble. We have a lot of bubble, just become a chain. So the main difference between the hifiasm algorithm and all other tools is that actually it has some graph tree binning strategy. That's just you want to use the trail markers, like some of the marker from the father and mother's genome. So in most cases, they are k-mers to label each side of a bubble. So if we look at example on the right side, so here we have the two bubble. So if we would like to get the two haplotype, we need to find the two parses that's from the left end to the right end. So there are 4 possibilities, right? What the graph trail being doing here is to color or label each side of a bubble, and then by looking at the color of the sum of the marker of within each side of a bubble, we would finally know that actually only the case 1 is the real result. So here I'm just showing a real, it's just a real genome. It's from the HT02. It's just a sub-region that we see it is still a chain of bubble. And there are many of the rays in red come from the mother. We call them maternal nodes, nodes actually. And we also have a lot of the nodes in blue come from the father. So if we would like to get the maternal haplotype, for example, that we just find the parts from the left end to the right end, including the most number of the nodes actually in red. So it's just like this. But in practice, there are a lot of the other heuristic strategy or some of the optimization. So it's just showing some of the simple example here, just to give you a sense. So the advantage of the graph trail binning or graph facing here in comparison with the pre-binning strategy we talked before is that it is more robust to handle different types of errors. So for this example, we could say that actually still that all the yellow nodes, all the blue nodes, actually they are heterozygous. They should be partitioned into either haplotype 1 or haplotype 2. But for all the green nodes, actually they are homozygous. They should be partitioned into both haplotypes. There is one mispartitioned node for the nodes 9, right? Or rays 9, yeah. It should be partitioned to both haplotypes. It is a homozygous rays, but for some reason, maybe due to some phasing error, it's just be partitioned into haplotype 2. So if we are still using the pre-binning strategy that we talked before, so actually the haplotype 1 cannot see the rays 9. So finally, we get assembly gap here in the haplotype 1. But if we are using the graph binning result here, we first get a graph. And by looking at the graph topological information, we know that race 9 should be automatically corrected. It should be partitioned to both haplotypes. So theoretically, actually, this method combines the information from globally from the parental data and also the local information within the assembly graph actually to get some better results. But the pre-binning strategy, like most of the existing method, actually, they lose all this type of graph information. So here I'm showing the result about our tools in comparison with all other methods. So the y-axis actually indicates the assembly contiguity is just the contiguity 15. So in most cases, the larger the better. So on the right side, I'm showing the human genome assembly result. We could say in all cases, actually, the hifiasm is better than all other tools. So on the left side, I'm showing the result about the non-human genome assembly. So especially for the huge red wool tree genome, its genome size is about 30 gigabase, which is 10 times larger than the human genome. Actually, only the hifiasm and the paragraph could finish the whole assembly procedure since this genome is pretty large. And but if we look at result, actually the hifiasm is much better than the paragraph if we look at N15 here. So for the running time, actually the hifiasm could finish the high quantity genome assembly in just less than 10 hours. It could produce about the reference level that actually the assembly quantity is quite comparable with the human reference genome. It's just using about 10 hours. Actually, it's very useful nowadays. Maybe for the personal genome assembly or something else. And for this huge red wool tree genome, actually it's also much better than before. I will then talk about how do we achieve the single sample haplotype result genome assembly with a high series, with the additional help of the high series. So the motivation here is that we figure out actually the main limitation about our algorithm is that it requires the parental information to do the phasing. So consider if we still have the real genome here, that we have a two haplotype, one from the father, another from the mother. So if we do not have any additional information, we just have the long rays, like the pi-by-hi-fi rays, ONT duplex rays. Actually, eventually we could just end up with two assemblies. So each assembly is random phase. The random phase means that actually some of the region come from the haplotype father and some of the other region come from mother. This is not the result what we would like to have. So our previous method actually using the trail binning phasing with the parental data to get actually the chromosome level phase assembly. but this parental data is not always available, especially in the clinical treatment or some biodiversity environment. Some animal or some plants just capture from the outdoors, something like that. So to solve this issue, actually, we additionally incorporate the high series. So I guess in most cases, the high series are the short reads. It's just the most case, but nowadays we probably also have the high C long reads. But here we just talk about high C short reads. So they are pretty short. If we look at the example on the right side, they are pretty short. They are still just Illumina short reads, but they could provide long-range information that could up to the 100 megabits. So in compression, actually the long reads, they are probably the 100 times longer, but they do not have any of the long-range phase information. So basically, we could combine both of them. So if we still have the real genome here, the high C read could help us to bridging any pair of the variants that even though they are far away from each other. So the key assumption for the phasing is that most of the high C read should bridging the variants from the same haplotype. So here I'm just still give the workflow of the hifiasm high C here. So the first step is still the error correction and then the doing assembly. The key difference is still the phasing, that we do some graph-based high C phasing that actually could help us to get the better result and do not require the data from the father and the mother. So just give an overview about the high C phasing within the graph actually here. So basically we have the three types of the input. The first input are the heterologous nodes. So if we look at example on the right bottom, that we say that for each side of a Bible, they are the heterologous nodes. That they are reconstructed by the PacBio long reads or some Oxford nanoparrays. Actually, they just capture some of the local phase information. And then we have these high C links that actually there are many of the dashed line are here. So they are bridging some of the heterologous nodes in between. Actually, they provide some long-run information. We call they have some global phase information. So they help us to cluster all the nodes within the same haplotype together. So the third type of information here is homologous pairs. We still call the local phasing. So homologous pairs here is still like the, say we have the homologous region from the same chromosome and from the different haplotype. They are highly similar to each other. It's just we talked before. So if we could still find some of the nodes within the assembly graph that are still highly similar to each other, so it is very likely that they are homologous to each other. So they should be partitioned to different haplotypes. So this information helps us to separate all the nodes to different haplotypes. So we could combine this type of three information actually to finally assign each of the heterologous nodes to either haplotype 1 or the haplotype 2. So finally, we should get the two sets. So one set for one haplotype. So that is the result what we would like to have. So in practice, we solve this as a max cut problem, but so the likelihood formation is like this, and this is not our new function. It just reuse some of the previous work. But actually, in practice, this max cut is NP-hard. We know that. Actually, we use some of the heuristic strategy to do some random flipping. So here, and just for this example, we have a nice graph, and we have a lot of the high C links. So we also have the homologous pairs. So what hifiasm doing here is just to first remove any of the homozygous, all these homozygous nodes in green, and since they do not contribute anything for the phasing, and then we convert this graph into a cut graph. So in the new graph, each node is still corresponding to the nodes within the assembly graph, but we have a lot of edges. Some of the edges are positive, some of them are negative, so they corresponding to the either the high C link or the homologous pairs. So finally, we could find a max cut that's to partition all the nodes into two sets. So actually, one set for one haplotype, that is the result of what we would like to have. So here I'm just showing the result of the our algorithm in comparison with the other tools. So for this graph, for this plot, actually, each dot represents one context. So the y-axis represents how many maternal markers within each context. That actually markers here is mostly for the k-mers, and the y-axis, x-axis represents how many paternal markers within each context. So if we first look at the hifiasm high C, this is actually our tools, and the Falcon Face high C. The reason that we say these two methods is just because that they have exactly the same input and exactly the same output. We say that the main difference between the hifiasm high-C and the Falcon phase high-C is that there are many dots actually within the Falcon phase high-C plot actually are in the middle. But for the hifiasm high-C, most of the dots are in the x-axis and the y-axis. The reason is that if we pick up the one dot actually in the y-axis, we could say that most of the variants or the k-mers come from the same haplotype. So which means it is a haplotype-resolved genome assembly. But if we pick up the one of the counting in the middle, we could say that many of the variants or the k-mers actually come from both haplotype. So they are not the haplotype-resolved genome assembly. They are not, which means the facing here is just the field. So we could say that actually, by looking at the results, the hifiasm high-C is better than the Falcon phase high-C. So we are also showing the hifiasm trio result here as a ground truth using the parental data. So basically, actually, these two plots are quite comparable. The main difference, is still that actually for the hifiasm trio that we could say that most of the dots actually around the y-axis actually have exactly the same color. It's also similar for all the dots actually around the x-axis for the hifiasm trio plot. But for this hifiasm high-C plot, actually we could say that color distribution is a little bit random. The main reason is that actually the high-C rays can only provide the facing information within the same chromosome. It cannot go across a different chromosome. So as a result, actually for this for the high-C phase assembly, actually the assembly may put the paternal haplotype of the chromosome 1 and the maternal haplotype of the chromosome 2 together. But for most of the downstream analysis of the applications, there is no requirement to put all the paternal haplotype of all chromosomes together or put the maternal haplotype of the all chromosomes together. So I would say that in most cases, if we do not have the parental data, actually this high-C phase assembly could perfectly replace the trio binding result. So on the right side, I'm also showing some result about the non-phase assembly. Actually, as we expected, there are many of the dots in the middle, which means they are not the haplotype-resolved genome assembly. I will then talk about some how do we achieve the telomere-to-telomere genome assembly. That actually is the ultimate goal for the de novo genome assembly. That's one contig for one chromosome without any gap. So the motivation here is still quite simple, that we say that for this long arrays, even though that they are much longer than Illumina arrays, but they are not long enough to resolve some of the challenged genomes of the region. So here I'm just showing the assembly result for the SMN1 genes. This actually within the highly repetitive region and about some clinical relevant genes. So on the left side, I'm showing that if we only have the pi-bar hi-fi arrays, actually for the assembly graph, we see there are many of breakpoints, which means that assembly cannot resolve this region. But with the longer arrays, actually the new assembly could fully resolve this region. We could say there is a very nice Bible here. So based on this observation, we could consider that if we could combine the advantage of the different type of sequencing technology to get the better result. So basically, specifically say that if we look at the IGV screenshot I'm showing here, so on the top track, I'm showing the pi-bar hi-fi array alignment result. On the bottom track, we see the ultra noisy array alignment result. We see that the ultra noisy array has a much more sequence errors than the pi-bar hi-fi array, right? But in practice, actually, this ultron array is maybe 10 times or more than 10 times longer than the hi-fi array, so we could combine both of them to achieve the better result. So here I'm showing the result about the hifiasm ultron. It's just some workflow overview. So the first step is still the error correction, and then we would like to build the initial assembly graph. But for this initial graph, it's we consider the information from both type of data, and then we do some graph simplification. It's actually, we have some more robust method to do that. So finally, we reuse the graph binning strategy that we talked before to get the haplotype-resolved genome assembly. So for the initial graph construction, like say, it's very important, since actually the most of the downstream analysis step are built on top of it. So if we look at the three examples, actually it's a three real examples. So for the first one and second one, actually they do not have any issue for the assembly graph, but for the right one, it is a broken subgraph. So as long as the initial graph has already been broken, so following step cannot recover it or reconstruct it. So it actually demonstrates that the initial graph is very important. So what we are doing here is to consider the ultra-long alignment information into the initial hi-fi graph. So if we look at the example on the right side, actually we encode how many ultra-long rays actually align through each side of each edge within the graph as additional cost or additional weight actually to help us to avoid the incorrect graph cleaning. And also it has additional advantage here to help us to remove some of the uncritical hi-fi rays, like especially for the red nodes in the middle, actually since there is no other ultron rays alignment goes through it. So after that, we have the very nice graph, and we just trying to map the ultron rays on top of it. So especially for this tangle region, most of the tangle region come from the segment duplication, centromere, or some repeats. Actually, this graph-based alignment will give us a sense how does each region should be resolved. So once we got the initial graph and we also got the alignment parses, actually we need to simplify the initial graph to a new graph that actually, this step is not so trivial. So most of the traditional methods are actually using some straightforward method to do that. They just find one begin node and find one end node and trying to find one parse that goes through this tangle. But in practice, actually, the human genome is not the haploid, it's the diploid. In practice, the two haplotypes might be tangled together, so it's actually involved a lot of heuristic strategy here. But if we look at the real human genome assembly graph, we could see it is a very large tangle, so this straightforward method cannot work well in some cases. So what we are doing here is to trying to encode each of the ultron rays that as parts of the nodes actually within the initial graph. So consider we have this graph here that each of nodes is still the hi-fi rays, and we also have the ultron rays aligned on top of it. So what we are doing is to convert each of the ultron rays from the hundreds of the kilobits to just a few integers. So here, especially if we look at the example of the U0 here, it's just a line through from the H0 to H3 and H2. So we are just convert it into an integer sequence that just including 3 integers. That's just H0, H3, and H2. So after that, actually, we just build a new graph on top of this integer sequence. So this is very lightweight and easy to be calculated. It's more like a downsample strategy, but keep all the necessary information in the downstream analysis. So after that, we have the two graphs. So one is a low-level graph for the initial graph, and then we have the new integer-based graph. Yeah. So we could merge both of them. Yeah, so finally, I'm just showing some results. Like this is actually for the compared with hifiasm and other tools like the work with another hybrid genome assembly. We could say that actually they are quite comparable for the high quantity data, but for the low quantity data, actually the hifiasm is much better, which means it's more robust. In some cases, actually, we could tolerate some of the low quantity data, low coverage. I guess it's mostly come from the robust framework that we talked before. And also, I'm just showing some of the efficiency of the hifiasm ultralong. It's just we show the computational cost that just using the Google Cloud. We could say that in most cases, hifiasm ultralong is probably the 6 or 7 to 10 times cheaper than the Verco. So it might be more useful for the large-scale sequencing project. So finally, I would like to thank my mentor and all the collaborators, and also without the help of the different consortium and projects, we could not get the valuable feedback and improvement. Yeah, I will stop here and thanks so much for the attention.